Welcome back to the video. I've got another exam walkthrough for you. This is from gravitational fields, and we'll be discussing the questions. And this is from, I believe, 2023. Let me just write it down. This is from CIE 2023 May-June variant 4.2. So that is the paper. So the first part of the question says, state Newton's law of gravitation. So here we have the answer, and the answer goes like this. The force is directly proportional to the product of the masses, and the force is inversely proportional to the distance squared. So that's something that we know. That's going to give you 1 point right there. Now the second point that you have to emphasize is that both of these masses, these m and this small m, the capital M, can be considered as point masses, which means we say that their entire mass can be just assumed to be as this point. Okay, so that's what we basically do. If you want to know a little bit more about this, you can go to the lecture videos that are there. They explain this in much more detail. Okay, so then it says a satellite is in a circular orbit around a planet. The radius of the orbit is r, and the period of the orbit is t. The planet is a uniform sphere. Use Newton's law of gravitation to show that r and t are related by the following. It's a pretty standard question. That's why we only have 2 marks available for this. We know the centripetal force is the gravitational force. The centripetal force is going to be mr omega squared is equals to gmm over r. This m cancels out. And then what I have is omega is equals to 2 pi by t. So omega square here, by the way, this is r square, I forgot to write r square right here. Then omega square is going to be 4 pi square by t square is equals to gm over r cube. Then I'm going to move this r to the other side. It's going to divide r cube, r square. Then this is going to move to the other side and divide, and you're going to get 4 pi square by t square is equals to gm over r cube. Okay, then I'm going to move things around, and I'm going to move this here, I'm going to move this here, cross multiply. 4 pi square r cube is equals to gmt square, and that is what they are looking for. Okay, that's the answer right there. Okay, I don't know what I did. Okay, let's move on to the next question. The next part says the Earth may be considered to be a uniform sphere of the following mass, and then they've given you the radius, and they have told you that the satellite is a geostationary satellite, which means its position relative to Earth is always 0, and the orbital time period is the same as Earth. Okay, so we already know a lot of information about geostationary satellites as well, so we're going to continue with the question, and we're going to assume, okay, we have geostationary satellite, its relative position to the Earth is always the same, so if the Earth rotates by 10 degrees, it's going to move by 10 degrees, and yeah. So it says, use the expression in part B to determine the height of the satellite above the Earth's surface. Okay, so let me just quickly draw it. Okay, now we're going to use the expression above. Now, one thing we have to be careful is when I say geostationary satellite, that means that the Earth's rotation, 360 degree, that time period is equal to the time period that the satellite takes to move around, t, okay? And the time period of the Earth's 360 degree rotation is equals to 24 hours. Okay, so I'm going to use that value. Now, we know the formula is 4 pi r cube is equals to gmt square. Now, I want to find the r, so I'm going to make r is equals to gmt square over 4 pi and then cube root. Now, let me plug in all the values. So we have square root 6.67 times 10 to the raised power of minus 11. Mass of Earth is 5.98 times 10 to the raised power of 24. Now the time period is 24 hours. Remember, for geostationary satellites, it's 24 hours. 24 hours into 3,600 is going to make it into seconds. And then we have 4, and then we have pi. So let's find the value of r out. Let's cube root. So the answer will be 4.22 times 10 to the raised power of 7 meters. Now this r, I'm going to write this as capital R. This r is this distance. Okay? And this is the radius of Earth, and this is the altitude. This is the altitude A. Let's call it HA. I want to find this HA, right? So I want to find this HA. So what I'm going to do here is just look at it carefully. This is the radius of Earth. This is the distance from the center of Earth to the center of this satellite. And this is the altitude, the height A. So R plus HA is equals to R, the R value that we found. Then R minus the radius will give me the altitude. So I'm going to just 4.22 times 10 to the raised power of 7 minus the radius they gave us, which is 6.37 times 10 to the raised power of 6. 6.37 times 10 to the raised power of 6 meters. I'm going to get a value of 3.6 times 10 to the raised power of 7 meters. Okay. So then it says another satellite is in a circular orbit around the Earth with the same orbital radius and period as the satellite in C. So this told you to find the angular speed, okay? And we know the angular speed. So we know you have to find the angular speed, and that's equals to 2 pi by t. Now we know that the satellite in C was a geostationary satellite, and we know that it has the same time period as Earth, which is 24 hours. Again, it's always like that for a geostationary satellite. It's also called the synchronous satellite as well in some of the textbooks and some of the books as well. Anyway, so you're going to put in 2 pi here, and then you're going to put 24 times 60 times 60, which is 3,600, and you're going to get 7.3 times 10 to the raised power of minus 5. So I'm going to write 7.3 times 10 to the raised power of minus 5, and the units here will be rad per second. Okay, now despite having the same orbital period, the orbit of this satellite is not geostationary. So very important that before you answer this question, you understand what's the difference between geostationary orbit and a polar orbit. Okay, so I'll go and I recommend revising that topic before you answer this question. Now, if an orbit is not geostationary, now we know geostationary orbits, they're always from west to east. Okay, so if the orbit is not geostationary, then this orbit, which is not geostationary, should orbit from east to west. So if this orbit is not geostationary, it should go from east to west. Okay, the satellite should go from east to west. Now, next thing, if this is not a geostationary orbit, if this satellite is not orbiting like a geostationary satellite should, then the orbit here might be a polar orbit. It will be polar. Okay, so this here is going to be your first point, and this is going to give you your second point. They've already told you the time period is the same, and they've also told you the same orbital radius as well. So those things you can't mention here. Okay, so that's it for this question. I'm just going to show you the mark scheme. So here's the mark scheme.